So in this chapter 5, we're going to be talking about, or we're going to begin by talking about trigonometric identities. And when we say an identity, what we're really talking about is like a mathematical statement, like an algebraic statement that's true for all values. So for example, if I said like 2x plus 6 is equal to 2 times the quantity x plus 3 is like an identity. Now it's a real dumb identity because like, sure, but you know, like that's an identity. That's always true for all values of x. Is everybody okay with what we mean there? So I've gone ahead and condensed the basic identities that we're going to be talking about all onto this one sheet for you guys. So this is in the content library. All of the identities on this sheet are things that we've ostensibly talked about either directly or indirectly. So, for example, we know that sine and cosecant are reciprocals of one another, right? So sine is equal to 1 over cosecant, or like cosecant is equal to 1 over sine. Everybody okay with that? So these first 6 identities are just the reciprocals that we've talked about a bunch of times. Okay. On the unit circle, we know that tangent is y over x. And on the unit circle, y is sine and x is cosine. So tangent can just be sine over cosine, right? And then equivalently, if we used these identities over here, we could turn it into secant over cosecant, but like that's a version that I'd almost never use, just FYI. Cotangent is the reciprocal of tangent, so if tangent is sine over cosine, cotangent is cosine over sine, right? So these next 3 are the Pythagorean identities. If you think about a circle that's centered at the origin, you take the x side and the y side and you make a right triangle, you have like x squared plus y squared has to give you the radius for the triangle, or for the circle, right? Everybody's okay with that? You take a circle centered at the origin, you pick a point on the perimeter of the circle, you make a triangle where the one side is the x coordinate, the other side is the y coordinate. You have a right triangle. Pythagorean theorem holds x squared plus y squared equals r squared, right? You take that fact down to the unit circle. X is cosine, y is sine, the radius is 1. So x squared plus y squared equals r squared becomes sine, or cosine squared plus sine squared equals 1, right? Everybody's okay with that notion? Again, things that we've already talked about, right? We're just kind of formalizing them here a little bit. Now, from that first Pythagorean identity, I can generate the other 2. If I divide both sides of this first equation by sine squared divided by sine squared is 1. Cosine squared divided by sine squared is cotangent squared, right? And 1 divided by sine squared is cosecant squared. Because 1 divided by sine is cosecant. Everybody's okay with that? Had I taken this first equation and instead divide both sides by cosine squared, sine squared divided by cosine squared is tangent squared, right? Cosine squared divided by cosine squared is 1. And 1 divided by cosine squared is secant squared. That's that. Okay with these Pythagoreans? Okay. The next one are the cofunction identities. Did you ever notice on the unit circle that if you did say like sine of 30 degrees is a half, and if you looked at the cosine of the complement of 30 degrees, aka cosine of 60, that's also a half. You might have noticed that on the unit circle. You might not have. We haven't mentioned that explicitly. But that's true always for all values of theta. So for example, sine theta is equal to the cosine of the complement. Remember that pi over 2 is just 90 degrees, so 90 minus theta is the complement of theta, right? Everybody's okay with that? So sine and cosine have that relationship. Tangent and cotangent have that relationship. And cosecant and secant have that relationship. In fact, the prefix co on cosine, cosecant, and cotangent is short for complementary, because sine and cosine are complementary functions. Secant and cosecant are complementary functions. Tangent and cotangent are complementary functions because, cotangent of theta is equal to the tangent of the complement of theta. Is that okay with everybody? Yeah. The last one, so when we were graphing sine, we observed that sine was an odd function, right? That was one of the things that we observed when we talked about graphing. Since it's an odd function, I know that f of negative x is equal to negative f of x, which is what we're seeing here. If sine is odd, then its reciprocal is also going to be an odd function, so we have the same behavior. Cosine was an even function. Since it's even, we know f of negative x is equal to f of x, which is what we're seeing here. The negative sign just goes away. And obviously, if cosine is even, its reciprocal is going to be even. So we see the same behavior here. And then we observed that tangent was odd. So f of negative x is equal to negative f of x. And obviously, its reciprocal, same thing holds. So those are the identities that we're going to be using kind of throughout this chapter. Let's go and do some examples of how we're going to use these things to answer or to do some problems now, okay? Okay, let's say we want to find the value for sine theta. If tangent theta is 3 and cosine of theta is negative. So first thing that I'm going to notice is that there's no identity that includes tangent and sine only. Right? If I looked at my list of identities, none of them involve just tangent and sine. I have tangent and cotangent. I have tangent with sine and cosine. I have tangent and secant. I have tangent and cotangent. None of them have just tangent and sine in it, right? So I know that I'm going to have to be using two of these identities somehow. The fact that I also know that whether one of them is positive or negative tells me I'm probably going to be using one of the Pythagoreans, because I'm going to use that positive or negative part to tell whether when we take the square root of something, whether it's positive or negative. So let's use our Pythagorean. It says 1 plus tan squared theta is equal to secant squared theta. If I know that tan squared theta is, or if I know tan of theta is 3, I can plug that in. So 1 plus 9 is 10, and when I square root both sides, I get that secant theta is plus or minus root 10. Everybody happy with what we did there? Now I know secant, if I go back and look at my identities, is the reciprocal of cosine. And since cosine is negative, I know I can drop the plus from my plus or minus. Right? That was one of the given conditions in our problem, was cosine was negative. Cool so far? Now I know sine and cosine. So I can say, okay, I know tangent is sine over cosine. So if I multiply both sides by cosine theta, I can say that sine theta is cosine times tangent. So if I plug in my negative 1 over root 10 for cosine and my 3 for tangent, I can just multiply those together and rationalize the denominators, or the denominator. I guess there's really, once you've multiplied them, there's only one denominator. And there's my value for sine. Aiden?
Can you just do like, isn't it the same thing as like using reference triangles, right?
Yes, unless the directions are asking you to use identities to find this, but sure, you could do the same thing doing reference triangles, absolutely. Amy? So for the chapter 5 test, I would give it to you, but we'll get a second block of identities later on in a future chapter. At that point, I would expect these ones to kind of be memorized, these common ones, but not immediately. Does that feel fair? Yeah. Okay. So that's one type of problem you'll be working on in like section 5.1. More so, though, what we'll be spending time in section 5.1 is doing simplifying problems. So if we're asked to simplify the expression, and we have these expressions involving trig functions, what we're seeking is like the simplest version for each of these trig functions, or these expressions, I should say. Really what that's going to look like is if you can knock this down to a single trig function, that's as simple as you can get, right? Right now I have two terms. Oh, and to do that simplifying, really we have two sets of tools. We can do algebra things like factoring or distributing or foiling or making common denominators. We can do stuff like that algebraically to combine things together or break things apart. And we can use our identities. So those are usually the two tools that I'm going to be looking at. And typically the algebra stuff is what I'm going to look for first. And then if I don't see an algebra thing, then I'd be looking at my identities. Not always, but like as you're getting started, that's typically where I'm going to go. So if I look at this, I have sine cubed plus sine times cosine squared. So first thing I'm going to look for is an algebraic thing. Do you notice any algebraic thing I might be able to do here? Drake?
This might be a stretch, but you could do something with the exponents, the sine cube and the sine, just like the regular sine. Probably do something between them.
Right. So what you've identified is that if I look at each term, I have two terms. They each have a greatest common factor of sine in them, right? So let's factor that off. Everybody feel okay doing that? That's just algebra. I didn't use any trig identity there. Let's look at what we have now. Do we see a trig identity that's there? Obvious, Aiden?
The Pythagorean identity, the sine squared plus cosine squared.
Yeah, so Aiden says, oh, sine squared plus cosine squared. I recognize that as part of an identity from the sheet. Sine squared plus cosine squared is just 1. And then sine times 1 is just sine. That's a single trig function. That's as good as you can possibly do. We're done.
Cosine, you just, they're both like over hypotenuse.
No. Easier than that. Sine squared plus cosine squared is equal to 1. That's all I did. So that green is just 1. That's pretty nice. The Pythagoreans are really good at making something complicated into something simple quite quickly. Let's do one more before we're out of time. So let's say we have secant x minus 1 times secant x plus 1 all over sine squared. Again, the first thing I typically look for is something algebraic. Is there any algebraic thing screaming at you? Amy?
Can you take out each of the values in the numerator?
Well, no, because you have this plus 1 and minus 1 rattling around in there, so there's not secants involved in all the parts there. Ellie?
Foil?
Yeah, I would FOIL this out, right? When I see something plus, like a plus b, a times a minus b, that's a difference of 2 squares. That's screaming to me, FOIL me out. So I get secant squared minus 1 time or over sine squared. So far, so good. What do you want to do now?
Good afternoon, Notre Dame Prep and Notre Dame Middle School. As we come to the end of the school day, I ask you to stop for a moment and reflect.
Let's finish this one before we head out, though, after prayer.
What can I do today to be a peacemaker? Or what have I done today to be a peacemaker? Did I get wrapped up in some drama today? How could I have handled it better? Lord, help me to be the peacemaker, never the one who stirs up more anger. You offer peace to me that the world cannot give. Help others to see that peace in me and long for it themselves. Have a good afternoon, Notre Dame, and God bless. Teachers, you may dismiss your students as you are ready.
All right, so what I would do is I'm going to use an identity. I'm going to use one of the Pythagoreans, and I'm going to replace the secant squared there with 1 plus tangent squared. And I'm excited to do that because the plus 1 and the minus 1 can just cancel each other out. What I'm going to do then is I'm going to think about this as really tan squared times 1 over sine squared, because I can rewrite tangent squared as sine squared over cosine squared. And then cancel the sine squareds. And I know that 1 over cosine squared then is just secant squared. You guys can go. Thank you for waiting for me to finish this one. I appreciate your courtesy.
I'll see you in a week.
Good luck with